wasn't blue, obviously.
Don't confuse them. Again, here, fluorine's more electronegative, taking more electrons. If we have a symmetrical molecule like fluorine gas, both of these atoms are trying to hog the electrons equally. So if I were to draw my net dipole arrow, not net dipole moment, we would have this fluorine atom is pulling in this direction, and this fluorine atom is pulling in this direction. They're both pulling equally. It's like a tug of war. So because there is the net value of these two pulling in opposite directions cancel each other out, this is a nonpolar molecule that doesn't have a net moment in any direction. So if I were to assign values to this, let's say that this one's pulling in this direction 3, this one's pulling in this direction 3, 3 minus 3 is 0, so this gives you a nonpolar molecule. Very symmetrical molecules like this exhibit this type of phenomenon where they are nonpolar, meaning that there is no side where you'll find electrons more than the other. Whereas in the first example, you'll find more electrons on this side than here, so it's kind of pulling in this direction. For this example, you have the opposite. It is nonpolar. It doesn't have a net. There's an area of the molecule where you'll find more electrons than the other. And you can make very, very complex molecules using this. A lot of people in like biochemistry like to look at really, really big old proteins and like to look at the surface of that protein to see, is there more electron density here, is there more electron density here, and that gives it very unique properties and how it reacts. So for those who are going into pharmaceutical chem, that's important. That's really important. So a scientist by the name of Linus Pauling was an interesting character. I'll say that much. In case someone read about it. Linus Pauling was the scientist who came up with this electronegativity. He created a numerical scale for electronegativity to quantify the polarity of a bond. Electronegativity of an atom can range from 0 to 4. There are periodic tables that have these values tabulated for each element. The polarity of a bond comes from the difference in electronegativity, the delta En between two atoms. This creates a continuous spectrum or range to determine if a bond is more covalent or ionic in character. So some periodic tables, I think there might be one in here that does that, I don't think so. They have these values tabulated for every single element on the periodic table. The most electronegative atom out of all the elements is going to be fluorine, as I stated. It has value of 4, like, period. And so, depending on the value that you get between two atoms coming together, you get this spectrum from 1 to 4, starting with 0, 1, 2, this is going to look a little bit off, 4, where if you have values between 0 and 1, then this bond is very covalent in character. Meaning that the elements, the atoms inside of that molecule are sharing the electrons equally so that there is no net numerical scale for that electronegativity. If we go from 0 or from 1 to 2, we have a polar covalent character. So this is a situation like hydrofluoric acid where we have a net dipole, where one atom is hogging the electrons a little bit more than the other atom. They're still sharing them. They're still sharing the electrons, but one is just kind of like being a greedy child. He wants all the toys. And then if we go from 2 to 4, well, in this situation we have ionic bonds, where pretty much one of the atoms is hogging the electrons so much that they're not even sharing it anymore. He's just taking all the electrons for himself and leaving the other atom to be as positively charged as possible. So that's a situation where we have a metal and a non-metal, like sodium bromide, sodium chloride, such and such. Let's draw some Lewis structures though. I'm going to use Professor Enderle's reader for this next part. I will be providing you guys with an online version of the table that I'm about to present to you guys. But for now, due to time, I'm going to present Professor Henderly's guideline on how to draw Lewis dot structures. So this is just a general guideline. So the first thing we want to do is you want to find the total number of valence electrons. And this can be, again, found by looking at the Roman numeral that's behind the A value on the periodic table. So hydrogen has 1, oxygen has 6, fluorine, chlorine, the halogen column is going to have 7, etc., etc. That's the first step you want to do. So you want to find out how many total number of valence electrons you have to play with to make bonds. The second step is you're going to draw the structural skeleton and fill with single bonds. So you're going to draw a molecule in which things are bonded to each other just with single bonds. Then you will fill in all valence electrons starting with the terminal atoms. So you'll work from the outside of the molecule to the inside of the molecule. For many of these examples, you have a central atom, an atom that's in the middle, that's surrounded by other atoms, and they're all bonded. And here we have a split. If the first condition is that we have extra electrons, then put them on atoms with atomic number greater than 10. The next step would be if more than one atom is less than 10, put electrons on the centermost atom. So then at that point, you're just going to put electrons in the center. The other split from this fill in all valence electrons is, does it have an octet? So you go here, you check these two conditions, you check this condition. They all lead to this octet rule right here. If the octet rule is obeyed, then all atoms have an octet and the Lewis structure is complete. You're done. If everything has 8 electrons around it, there we go. If everything has 8 electrons around it, then it follows the octet rule, then your structure is complete. The only other thing you have to do after you've completed your octet Lewis structure is consider if there's any resonance structures. And I have an example that's going to exemplify this. If it doesn't follow the octet rule, then what it means is some atoms don't have an octet, not hydrogen, metal, or part of the boron family. Find a lone pair on a neighboring atom, remove it, and make another bond. So when I drew the Lewis dot structure for carbon monoxide, that was the carbon with oxygen, I initially had a double bond. The carbon did not have 8 electrons around it, so it wasn't happy. So what I did is I took 2 electrons from the oxygen and I moved it to make a new bond, then my carbon was happy. So whenever you find yourself in a situation where one of these atoms doesn't obey the octet rule, you simply should start making bonds. Like I said, I will make a table for you guys as well that you guys can use. Let's go over some tips really quick. Zoom out. Again, always count electrons, the valence electrons using the Roman numeral of the A columns. Don't use the B columns. Hydrogen atoms are almost always terminal. So if you have a molecule that has a hydrogen atom, you almost always write it on the outside. It's going to be on the outside, it's never going to be on the inside. You're never going to have multiple things bonded to a hydrogen because it can only really have one bond, one single bond. Carbon atoms are almost always internal, meaning that they're in the center. Halogens are mostly terminal, meaning that they're at the ends, just like the hydrogen. Oxygen atoms can be both. They can be terminal or internal. They can be terminal or internal. That's right. Sorry. So they can either be at the end of your molecule, like the arms, very end, or they can be the center of attention. After sketching the molecular skeleton, fill valence electrons starting from the outside atoms to the inside. So you want to start from the outside to the inside. And hopefully by the time you get to the inside, you'll have no more electrons to play with. I'll have examples to show this. Check your octet rule. Make sure that all the atoms have 8 electrons around them. Issues against the octet rule can be fixed by moving electrons from neighboring atoms to make new bonds. And finally, hydrogen. I haven't really talked about this. I'm sure somebody, if we were talking about this in class, I'm sure somebody would be raising their hand like, wait a second. Hydrogen is an exception to the octet rule in that it only wants 2 electrons, not 8. So if we go to our periodic table, I'll talk about resonance structure in just a second. If we go to our periodic table, hydrogen wants to be like helium. Hydrogen has one electron, so if it has one more electron, it has no gas configuration of helium. It's not going to want 8, it just wants one more to be 2. Everything below this is a situation where you're going to want 8 electrons for molecules that obey the octet rule. And then finally, we have resonance structures. For those who are continuing on to organic chemistry, I cannot stress this enough. This is important. This is really important. There are many organic structures that present themselves with resonance structures. And so a resonance structure is formed where the skeleton of the molecule remains unchanged, meaning the placement of where the atoms are in the molecule doesn't move, but the locations of the electrons may change. All reasonable resonance structures follow the octet rule and have good formal charges. Well, what in the world is formal charge? My notes are all over the place now. What have I done? So, talk about resonance structure, now we're going to talk about formal charges. Formal charge is the charge assigned to an atom in a molecule assuming the electrons are equally shared between atoms. The best formal charge is 0, but plus or minus 1 is also acceptable. Any other value is unacceptable and indicates Lewis structure is incorrect. There is a formula for this, and books like to present this in a very, very complicated manner, and I'm going to show you a very, very easy way to do it. The formal charge of an atom, abbreviated FC, is equal to number of valence electrons for a free atom. So if I were to talk about oxygen, oxygen has 6 valence electrons, so you would put 6 right here. Minus the number of valence electrons assigned to the atom or molecule. In the molecule. So basically, what you do is you count, you look at the periodic table, look at oxygen, you're like, it has 6. It has 6 valence electrons. Then you go to your molecule, you look at where the oxygen is, and you count how many things are around that oxygen, and you subtract that, and that gives you the formal charge. And we'll do some examples at the very end of the class. The nice thing about the formal charges is the sum of the formal charges of each atom is always equal to the overall charge of the molecule. If the formal charges sum up to a different charge of the molecule, you done goofed. The formal charge is incorrect. You did something wrong somewhere. Maybe the structure is wrong. Maybe you should have put a 5 down instead of a 6. Who knows? But if the overall charge of the molecule is not equal to the sum of the formal charges, then something is wrong, inherently wrong. Let's do some examples. We're going to give the Lewis-Gauss structures for the following molecules. All right, so the first one we're going to do is, let's do HF. Let's do HF on, let's do a blank piece of paper. We'll just keep going back and forth like this. So the first thing I want to do is I want to determine how many valence electrons are in hydrogen and how many there are in fluorine. So hydrogen has 1 valence electron, so I'm going to put, let's see, total, oh my god, total valence electrons. We have 1 for hydrogen, we have 7 for fluorine because it's a halogen. So we have 8 electrons to play with. So I'm going to draw my fluorine atom first. We're going to do the skeleton. And I'm going to bond this to the hydrogen by drawing a line. So right now, I've used up 2 electrons to make this bond. This is a single bond. A single bond has 2 electrons. If I were to draw another line, that would be 4. Each line comprises 2 electrons. So you draw a bond, you subtract 2 from this. Now you have 6 electrons to place around atoms in your molecule. We know that hydrogen only wants 2 electrons around it, so hydrogen is happy. You shouldn't have to put any more electrons around this, but fluorine's going to want 8. Right now it has 2 around it. So 8 minus 2 gives you 6, which is just so happens to be how many electrons we have left over. This is your final answer. Fluorine has 8 electrons around it. Hydrogen has 2 because it's hydrogen. It goes against that 8 electron rule. This is the Lewis structure of hydrofluoric acid. All right. Let's do. So we did this one. Let's do nitrogen gas. Scoot up. N2. So total number of electrons. Total number of valence electrons. So if we look at nitrogen on the periodic table, let's see now. Looks like it's 5 because it's 5A. So we have 5 valence electrons per nitrogen atom. So we have 2 of them, so it's going to be 2 times 5. That gives us 10 electrons to play with. There is no central atom for this. We just have 2 nitrogen atoms, so we're just going to draw a nitrogen bonded to a nitrogen. So we've used 2 electrons to make this bond. So now we have 8 electrons to play with. So we have several different ways to figure this out. What I'm going to do first is I'm going to put 8 electrons around both of these nitrogen atoms. So I'm going to do 1, 2, I'm going to evenly space them out. So I'm going to put 4 in one nitrogen and 4 in the other. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Let's count how many electrons are around each nitrogen atom. 1, 2, 3, 4, 5, 6. This nitrogen has 6. 1, 2, 3, 4, 5, 6. This nitrogen has 6. They are not following the octet rule. So remember from the guideline, if one of these atoms is not following the octet rule, then we need to make some bonds. We need to pull electrons from something, from another atom to make bonds so that we can follow the octet rule. So what we can do is, if we move these 2 electrons here and make a bond, and move these 2 electrons here and make another bond, a triple bond, then the resulting structure is going to have 8 electrons around each nitrogen atom. So I'm going to draw an arrow like this, an arrow like this, meaning that I'm moving these electrons from here to make a bond. So now we should have 3 lines, not 1. 1, 2, 3. And these 2 stay put, so I'm going to put them on this side. And these 2 stay put, so I'm going to put them on this side. So now let's count the number of electrons around each nitrogen atom. We have 1, 2, 3, 4, 5, 6, 7, 8, so that nitrogen's happy. 1, 2, 3, 4, 5, 6, 7, 8, that nitrogen's happy. This is the correct structure for nitrogen gas. It is 2 nitrogen atoms with a triple bond in the middle of it. Let's use this as an example. Let's find out what the formal charge is for nitrogen here and this nitrogen. So let's do the formal charges for both of these. Let's call formal charge of nitrogen 1, which is going to be the left nitrogen. I'm just going to, just like that. And so the first thing to determine formal charge is put down the number of valence electrons the element has on its own. That's 5. Minus how many things are around that nitrogen atom. So we're going to count 1, 2 electrons. But instead of doing 1, 2, 3, 4, 5, 6 electrons for the triple bond, we're only counting half of the electrons. So it's going to be 1, 2. We're going to treat each bond as 1 electron for this. 1, 2, 3, 4, 5. 5. Formal charge of that nitrogen atom is 0. Let's do the formal charge of the right atom. So let's do left, and right. Again, nitrogen has 5 valence electrons. In this molecule, this nitrogen atom has 5 things around it. 1, 2, 3, 4, 5. 0. The net sum of all the formal charges in a molecule should equal the charge of the molecule. Nitrogen gas is uncharged. It's just N2, doesn't have any charge. So 0 plus 0 better equal 0. So we know that our structure is correct. All right. So we did nitrogen. Let's do ammonia. Dan, what time is it?
11:25.
What time did I start?
Yeah, that's a good question.
Oh, okay. So let's do ammonia. All right, let's total valence electrons. Nitrogen, again, we just figured that out, that was 5. We have 3 hydrogen atoms, in which each atom has 1 electron. So we have 5 plus 3, because 3 times 1 is just 3. We have 8 electrons, like that. From our tips and guidelines, we said that hydrogen is usually always terminal, so we're not going to draw hydrogen in the center. We're going to draw our nitrogen in the center. And now we're going to surround this nitrogen atom with the 3 hydrogen atoms. So we're going to draw 3 bonds. 1, 2, 3. Hydrogen, hydrogen, hydrogen. So now we've used 1, 2, 3, 4, 5, 6 electrons. So now we only have 2 electrons to play with. We can't put these 2 electrons on our outermost, working from the outside in on the hydrogens, because the hydrogens have 2 electrons each, they're happy. So we're going to put these 2 electrons in the central nitrogen atom right here. Now let's check if our octet rule is obeyed. The hydrogens have 2 electrons, 1, 2. This one has 2, this one has 2, so these are happy. Our nitrogen atom should have, again, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So this is the correct structure, the Lewis substructure for ammonia. Later in the class, we're actually going to draw the 3-dimensional structure of this, where you actually get to see how it orients itself in 3D space. It's going to look a little bit different, but very similar. Let's keep that up. We still have space on the bottom of this page that we can use. All right, so we did ammonia. Let's do methane, CH4. And total. If you want to work ahead, and you can then go back to the video and check if the answer is correct. Carbon has 4 electrons, because it's 4A on the periodic table, plus 4 times 1. So we have 4 plus 4 giving us, again, 8 electrons. Our hydrogens are going to be terminal, meaning that our carbon is going to be in the center. We put carbon in the center with 4 hydrogen atoms around it. 1, 2, 3, 4. Each bond uses 2 electrons. We have 4 of them. So we have 2 times 4, so we've used up 8 electrons, meaning we have no more electrons to use. Does that mean the structure is correct? Well, let's check the octet rule. Hydrogens have 2 electrons, so they're happy. Our carbon has 8 electrons around it, 2 for each bond. So this is the correct structure for methane, the Lewis structure. All right. That was funny. Let's replace the hydrogens with the halogen. So we did methane. Let's do carbon tetrafluoride, CF4. Carbon again has 4, plus 4 times. If you look at fluorine in the periodic table, it's going to have 7 valence electrons, so we're going to put a 7 here. So it's going to be 4 times 7, which is 28. 28 plus 4 gives you 32 electrons. All right, so we're going to put, we know that the halogens, based on our tips, said that they should be terminal, so they're going to be on the outside. We're going to put carbon in the middle again, just like in methane. I'm going to put 4 things around it for each of these atoms. 1, 2, 3, 4. Okay. Now how many electrons have we used? We used 1, 2, 3, 4, 5, 6, 7, 8. So we use 8 electrons to make our bonds. 32 minus 8 is going to be 24. Okay? So we want to use these 24 electrons. We need to put these in the molecule. Let's start from the outside in. This time, we don't have hydrogen on the outside. We have fluorine. Fluorine wants to have 8 electrons around it. So this fluorine atom has 2 electrons right now, so it wants 6 more, so we're going to put 1, 2, 3, 4, 5, 6. So I've used up 6 of these 24, so I'm down to 18. Let's use another 6. Now this fluorine's atom, now we're down to 12. This fluorine has 8 around it now. We're down to 6. And I've used the last 6 on this bottom fluorine atom. So now I have no more electrons to play with. Let's check to make sure our octet rule is obeyed. 1, 2, 3, 4, 5, 6, 7, 8. Fluorine's happy. 1, 2, 3, 4, 5, 6, 7, 8. That fluorine's happy. That one has 8 around it. This one has 8 around it. And our carbon has 8 electrons around it. This looks like the right answer. I think we're done. Dan is just smirking over there. Let's use it. All right, now CF4. Let's do nitrogen oxide, NO+. So this is going to be positively charged. So this is the first example where we have to worry about the charge of the molecule getting in the way. NO+. Total valence electrons. So earlier when we did ammonia and N2, nitrogen has 5 electrons. Oxygen is right next to nitrogen in the periodic table. It has 1 more electron, so it has 6 valence electrons. And this is where some people get tripped up. They look at this and say 5 plus 6, there's 11 valence electrons that I can play with to make this molecule. Stop right there. No, don't stop the video, Dan.
Just try to do what you tell me to do.
Because we have a positive charge, this molecule doesn't have 11 electrons. It's going to be 5 plus 6 minus 1 because it's positively charged. If this was a negative value, like if it was NO minus, then I would be adding more electrons. Remember, we're determining how many electrons are in the molecule. We have 5 for the nitrogen, 6 for the oxygen, and then because it's positively charged, we're losing 1. So it's going to be 5 plus 6 minus 1, which gives us 10 electrons. We have 10 electrons to play with. So first thing, let's draw a bond between the nitrogen and the oxygen. No. So we've used up 2 electrons to make this bond. So now I have 8 electrons to play with. So I'm going to evenly space out my 8 electrons between these 2 atoms. So again, it's going to look a lot like the dinitrogen molecule that I did in the very beginning. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Let's check if it follows the octet rule. Nitrogen, 1, 2, 3, 4, 5, 6. Has 6 electrons, not happy. Let's check the oxygen. 1, 2, 3, 4, 5, 6. Has 6 electrons, it's not happy. So we need to make some bonds. I'm going to move, again, these 2 electrons here, these 2 electrons here, to make a triple bond. One, 2, 3, 4, 5, 6, 7, 8. Nitrogen's happy. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy. And then finally, because this molecule is charged, don't forget to put your brackets, put the plus sign, because it is a positively charged molecule. All right, let's do the formal charge for all of these atoms, or these 2 atoms. Not all. It's not like there's like a million of them. Let's do the formal charge of nitrogen first. Nitrogen has 5 electrons on its own, based on the periodic table. And it has 1, 2, 3, 4, 5 things around it. So the formal charge of this nitrogen atom is going to be 0. Let's do the formal charge of the oxygen atom. Oxygen on its own has 6. And this oxygen atom has 5 things around it. 1, 2, 3, 4, 5. Meaning it has a formal charge of +1.